My topic is Introduction to Plasma Monitoring using Optical Emission Spectroscopy with Machine Learning. Here are contents in this presentation. As the size and complexity of semiconductor devices increase, the number of process steps also increases. If the yard of individual processes does not increase it, the overall yard of the process decreases below 50% as the number of process steps increases. This necessitates the demand for technology to improve yield in semiconductor manufacturing processes. Plasma processes are commonly used in semiconductor manufacturing, but predicting the result is difficult due to the non-linear relationship between process variables and outcomes. Therefore, to know the actual results after completing the process, it is necessary to directly measure the characteristics of the product, resulting in a delay time. This delay shows down the detection of process abnormalities, linked to a decrease in yield in subsequent processes. Therefore, by predicting the result or determining abnormalities without directly measuring the characteristics of the product, it is possible to eliminate the delay time and prevent a decrease in yield through immediate feedback on processes. Diagnostic sensors for monitoring plasma processes can be broadly categorized into invasive and non-invasive approaches. Invasive approaches utilizing probes allow direct measurements of plasma characteristics but can influence the outcome of process. On the other hand, one type of non-invasive approach called optical emission spectroscopy can measure not only the physical properties of the plasma but also information about the chemical species without significantly affecting the process. However, OES present a challenge in analysis due to the real-time input of multivariate data. In the bottom left case, the OES signals for normal and abnormal processes are depicted, but it is difficult to visually identify the differences. Therefore, real-time analysis of multivariate optical signals through machine learning is required to diagnose process abnormalities and analyze the root cause of the fault. But using without knowing the plasma characteristics has the limitation for delicate process. For example, as the representative characteristics, the electron temperature shows you how much energy electrons have in plasma, and this affects the dissociation rate of the gas in the plasma, resulting in the difference in reaction rate. The second one is electron density, affecting the processing rate and condition. These characteristics depends on the equipment even under the same conditions, so the monitoring these characteristics is important. Below table shows the method for the monitoring divided into two categories, which one affects the process when monitoring, the another one doesn't. One of the problems for plasma monitoring is alternation in the inductively coupled plasma. Above figure shows the scheme of ISP, which applies the power to the plasma in the way of inducing with antenna coil. And this plasma generating equipment shows two distinct modes. The one is E mode, which applies the power into the plasma in axial. The other is H mode, applying the power in helical. When we increase the power in ICP, the mode transition occurs with sudden increase of electron density and decrease of electron temperature. And this discontinuous phenomenon hardens the difficulty of fine process efficiency control. So monitoring the change of characteristics in the mode transition is important to make better process equipment. Cause for the mode transition covered in the literature is non-linearity in power exertion. The power absorbed by the plasma isn't exactly the same with the power applied to plasma. As shown in left figure, the absorbed power in plasma increases with electron density in non-linearly. The process condition covers is in the intersection with lost power. The point, the lost power and absorbed power are balanced. And this shows the discontinuous change in mode transition. Below shows you how the increased power increases the electron density. The first one, increased power, increased electron energy having bigger collisional cross-section makes more gas ionized, making more electron. The second one is increased multi-step ionization from metastable, the easy way of ionization process for electron. Here is the table that summarizes the paper for each mode transition reviewed. This could be categorized in two sections. The one is the paper show each mode transition from the perspective of increasing the collisional cross-section, and the other is increase of metastable that create the stairs for the electrons to facilitate the ionization reaction. The mode transition could be varied with the process pressure. In low pressure, the required power for mode transition decreases and increases in high pressure. And also, the gas composition could affect the power required for the mode transition. As the composition of the other gases increases, the required power increases from the quenching effect. One of the equipments for monitoring plasma is Langmuir probe. The probe is equipped in the plasma and measures the current change in probe potential. This probe can show the change of plasma characteristics in mode transition like plasma density, electron temperature, and electron energy distribution function. But this method is invasive to plasma, which can affect the experimental result and processes. So, optical emission spectroscopy, the non-invasive way using optical characteristics of plasma, goes more important. The OES measure intensities of the light emitted from the excited gas molecules and atoms. The light figure shows the measured intensity from OES. The important thing is the interpretation of the data from OES. The representative methods are line ratio and actinometry. Line ratio is method using the information about collisional steps and chemical reactions steps of molecules and atoms, but this interpretation have still limitation. More researches are needed. To diagnose the process variables that cause process abnormalities in real time through OES signals, it is necessary to understand the nonlinear relationship with the optical signals as mentioned earlier. However, the interpretation of nonlinearities such as collisional radiative mechanisms and power absorptions within the plasma has limitation when relying solely on domain knowledge. Therefore, methodologies have been studied to apply machine learning for the interpretation of nonlinear relationships and the diagnosis of process abnormalities. These methodologies aim to overcome the limitation of traditional interpretation methods and enable the application of machine learning for process abnormality diagnosis. Various machine learning technologies such as PCA have been studied for abnormal diagnosis and root cause analysis in plasma processes. However, these methods had limitations in accuracy because they couldn't capture the nonlinear relationships between the output signals and process variables. To overcome this limitation, methods using autoencoder are developed, but they couldn't explain the relationship between the analysis result and the actual process variables. In this study, we utilized the autoencoder to extract relevant features variables related to the actual process variables from the input optical signals. This allowed us to conduct abnormal diagnosis and root cause analysis in the process. Autoencoder is one type of artificial neural network and consists of encoder layer and decoder layer. When input variables passes through the encoder layer, they are represented by a smaller set of virtual variables called jet features. These jet features, which represent the original data and then used to reconstruct the original data. The accuracy of the reconstruction improves as the jet features contain more information about original data. By raising this property, autoencoder can extract the underlying jet features of original data. In contrast to PCA, which has been frequently used in plasma process monitoring, but has limitation in presenting the nonlinear characteristic of plasma, autoencoder can capture this nonlinear characteristic through the activation function in each layer, resulting in high accuracy. The conclusion is monitoring the plasma characteristics becomes more important, but because the increasing demands for the semiconductor process efficiency. One of the nonlinearity in plasma is mode transition in ICP. Mode transition shows the discontinuous change in plasma characteristic make it hard to control the process efficiency. Plasma process can be monitored in Ranger probe and OES. And OES shows the plasma characteristic in non-invasive way, but need more researches. Machine learning can extract the plasma property in data-driven model, but there is limitation in extract the plasma property in non-linearity. So autoencoders, neural network like autoencoder are researched for extracting of the plasma property in non-linearity.